Thanks for the introduction, Kate. Today I'm talking about GLEAM, and this is an illumination estimation framework for real-time photorealistic augmented reality on mobile devices. So why do we care, right? Well, the name of the game here is giving our physical objects the same properties as our virtual objects. And so that gives your virtual objects a sense of belonging inside of these physical spaces, so that you can generate virtual objects that look very much like those real objects. So that's what we're trying to do here. Because augmented reality is really great, you're able to place physical objects in the right spaces. Geometrically, you can place them in those right spaces, so you can catch your Pokemon, you can see your couches and how they match your drapes. And what we've been using it for has been for some things like data visualization, where you can look at the map data and you can walk around and point your phone through it and see the vendor data through the Phoenix area. This has been of interest to the ASU Office of the President, so they can see who's hiring our students, for example. Or you can use this for education. This is Dr. Tanya Harrison at the REMARS conference, Jeff Bezos' AI ML conference, and she's gesturing around in midair, but what she's actually doing is using this HoloLens to trigger animations of the Curiosity rover, and what the audience is seeing is this Mars rover there, and Ali is using this iPad in order to create these scenes. And so these kinds of different augmentations are able to combine these different worlds together, these physical and these virtual worlds together. And so that's really nice, but it turns out that if you're just placing these objects in the right spaces, it's just not enough. You can look at when you place these different elephants with different materials on them, you're seeing these kind of glows around them, and that's because they're using this lighting that was imbued by the developer at runtime, and it doesn't match the lighting that's reflecting off of these glasses, that's reflecting off of these plates. Instead, it would be much better if we were able to imbue the physical lighting inside of that virtual environment. So we need to be able to estimate that physical lighting so then we can then put it into the virtual lighting. Are you able to load that app up? Yeah? Okay, cool. So elephant on the top over there. So we're able to actually now see a lot more. Now, it's hard for you to see through this smartphone onto the iPad, so I do recommend you check out the demo itself. It really creates these kinds of experiences that you can. The point here is that we want to be able to estimate physical lighting so we can generate that realistic immersion for these virtual scenes. So again, with no light estimation, again, some materials work well, like wooden types of materials, but when you've got any kind of specularity, like marble surfaces, or especially metal type surfaces, shiny metal surfaces, you're going to want to have some kind of estimation. And so what ARKit and ARCore, that's Apple and Google's solutions thus far, they've been estimating illumination through the camera. The camera can understand the scenes, the point cloud of the scene, and so where things are geometrically, and it can take those textures from the camera and push them down into the virtual environment as well. But from a single camera frame, you're only seeing a very limited amount, right? You're seeing what the camera sees, right? It's a very limited frustum, right? So what they use to build on that is to use machine learning to fill in the gaps. And what you see as a result there is, look at that metal elephant on the left, you end up seeing a little bit of that training data set in there. There's a blue sky in there. Looks like there's a bush and a tree there. That's influencing their inference as well. So we're doing something a little bit differently here, and that allows us to imbue our elephants with this virtual lighting. We're not arming our elephants either, though, Ben, so sorry about that. But anyway, what are we doing here, right? What we want is for these reflections to match the reflections of these objects in the scene. So like that hammer, like that pen, like this duct tape, right? The illumination should match. And so what we said is, well, if you look at these kind of reflective objects, they actually tell you a lot about that lighting. So why is that? Well, it's because these reflective objects reveal highlights, shadows, and colors depending on the surfaces of those surfaces. And so we're going to pull a page from the graphics community, from the CGI community that's been really active in the film industry and making these virtual CGI elements look like they belong in your Avengers movies. And they use a technique called light probe estimation. What we're doing here is integrating that kind of light probe estimation with mobile augmented reality tracking and with these mobile systems trade-offs so that it can run really smoothly and efficiently on our mobile devices. And that can make things look really nice. And so to do that, we built this system called GLEAM. GLEAM is an acronym. It stands for Generating Light Estimations for AR on Mobile Systems. And it's this 3-element system here. We do radiant sampling, network transfer, and cube map composition. So to do this radiant sampling, we're using the tracked AR camera position. So augmented reality is built on this understanding of where is the camera with respect to your physical scene. If you know that, then you can create this illusion of putting these virtual objects in the right places. And so we know where the camera is with respect to the scene. And so if we also know where there's a reflective mesh in the scene, maybe this metal ball, maybe some other mesh, then we're going to know how to generate this reflective geometry. So what we end up doing is shoot a ray out of the camera through a pixel until it hits a metal surface. And we reflect virtually off of that metal surface using just the laws of reflection and know where the angle at which the light is incoming onto that surface. And we know that value of the pixel, and that represents the intensity of the light. So suddenly we've collected a sample of radiance that's tying the value of that illumination to this particular angle. And so every single pixel that you see there of that metal ball is one of these radiant samples, because we're able to reflect off of the ball and find that angle and map that to that pixel value. So that's how we collect these radiant samples. And then as an optional stage, if you've got multiple devices, they can share these radiant samples with each other, and then you can collect a more rich lighting estimation, which is really good for things like museum exhibits or classroom experiences where you've got multiple devices together. To complete the task, we take those radiant samples and we interpolate them into this illumination cube map. We use nearest neighbor algorithms, inverse distance weighting algorithms. You can find the details in the paper, of course, and they interpolate the missing gaps in order to fully complete this cube map there. Cube maps, for those of you who aren't familiar with that, that's a representation of a 360 environment. It's just mapped to these sides of the cube. And so you can unroll it like that middle figure there. So all this is done so that we can generate these light estimations for AR on mobile systems. Now, a big part of the work is about trade-offs between the number of samples, the freshness of the estimation, the update rate. We played a lot with these different trade-offs, turned a bunch of knobs. Please read the paper for more of those details. I just don't have the time to do it today. We implemented this in the Unity game engine, and I actually don't have the time to talk about these details either. But the short story is that we use this multi-thread approach. We don't want to do anything on the main thread. We want to do as little on the main thread as possible so that we can keep it at interactive frame rates. And then we can do the heavy lifting on an auxiliary thread. And so we do that separation, and we do implement it, and it works quite well. And it works quite well. Single viewpoint interpolation, when you look at that metal ball there, each of those pixels becomes one of these samples in that cube map space, and then we can interpolate it together. Now, it doesn't work well at the far side of the ball. As you start to approach the angles that are on the outskirts of that ball, you're seeing that it's sparser and sparser sampled. You're seeing that fleur-de-lis kind of look there at that right side of that cube map. And what that results in is these imperfections on the far side. But if you've got multiple viewpoints, then you can cover that by having more radiant samples on the other side. And so your multi-viewpoint interpolation works even better. And so this is kind of an optional thing to further improve GLEAM. At the end of the day, this is what it ends up looking like. You can do a shot-for-shot comparison. And you can see this specular bunny rabbit there, and it's a green bunny rabbit, and you can see the marble figure there. And you can even see that even plastic things, like this plastic plane, are illuminated better when they actually imbue that physical illumination inside of this virtual scene. So it works, we felt it worked quite well, but in order to really convince our reviewers, we have to run a user study, right? And so we did a user study of 30 people. And we asked them about the richness, the fidelity, and the adaptiveness of the scenes. And we constructed this around this kitchen scene, which had a lot of specular objects, and a living room scene that didn't. It had more matte surfaces involved. And what we found was that, as we expected, GLEAM really improved the lighting perceptually for these specular items. And you can see that it really outpaced the directional side. The directional lighting is pre-baked directional lighting. But something that we didn't expect, and looks actually a little bit like a negative result here, is that the directional lighting, some of the users preferred it. It looks like it was a toss-up, and some users actually preferred it more than GLEAM, and that's fine. And we suspect, given our user interviews, that a lot of that is because the directional lighting that the developer has put in there beforehand will preserve the visibility of the scenes even if you're in kind of a dark environment. As you probably saw this, we used a stage environment. It's called the intelligent stage at ASU, and it allows us to control the DMX lights overhead and incandescence around. So we were able to have some dynamic lighting as well as some static lighting in our user study. Again, paper details. So we did those comparisons against these pre-baked lighting. We also did the comparisons against ARKit. We did single viewpoint GLEAM to be fair against ARKit, and GLEAM seems to outperform ARKit both in correctness as well as its adaptation to dynamic lighting changes. It is a toss-up for some people. Some people did prefer ARKit, and some people said both are fine, right? And so to really see why, let's take a look at this video. And it's showing GLEAM first. And you're seeing GLEAM update in real time as they're walking around. And I like this video because you can see, I'm pausing it here. When Linda walks in front of that light, she's casting a shadow on these pots and pans, and GLEAM is capturing that. Right? GLEAM is able to know that she's standing in, she's occluding the light from her physical scene, and so the virtual scene also has that light occluded, so that shadow is then cast. So it gives that sense of immersion, really. And as she continues to walk around, you know, the light gets revealed again. And this is multi-viewpoint. Linda's there, Ali's there walking around. And you can see that's working quite well. And so the user said GLEAM provided better reflection as it adapted with the lights pretty accurately. At least that's what that user said. When it comes to ARKit, the reflection was more clear. I'm going to pause here again. You can see that it's actually quite rich in its reflection. They get more pixels because they're able to use the entirety of the camera frame. We're only using the pixels that we see on top of that metal ball. They're able to use the entire frame, which is really great. It allows for that richness. Oops. Oh, boy. Let's skip to where we were. But the problem is that occasionally you see random blue lights, random yellow lights in the pots and pans. Here, I'll pause here. You can see the sky. There's not a sky in the eye stage. That's just an artifact of that machine learning there with ARKit. And so, you know, they work well in some ways and not in others. But you can see that it does provide these rich estimations. You can also see that they update very slowly. It's about 3 to 5 seconds, depending on kind of what's going on with the computational device at the time. It's a little bit slower than what GLEAM is doing, which is updating in real time. So the takeaways here are that the illumination estimation really expands the material palette. Your developers can now use more materials. They don't have to limit themselves to the matte materials where they know what to where they can only put in the expected lighting. They can now put in specular materials that will look like they belong to the right scenes in these physical environments. And this enhances the immersive potential for augmented reality. So these specular materials and environmental shadows now can become part of this augmented reality. And GLEAM can work robustly and in real time, outpacing the state-of-the-art ARKit and ARCore techniques. Now, it must be said, GLEAM needs to have one of these tracked shiny objects, which means you have to know where that object is in space, and you need to have that object to begin with. And we've used a metal ball. We've also used that metal elephant itself as a light probe. As long as it presents some kind of convex surfaces to your camera, then it works well as a probe. So we can integrate this into different kind of VR controllers, AR controllers, and into the museum exhibits themselves as well. So it allows for that kind of exploration. What GLEAM also allows for is this multi-viewpoint estimation, which further improves the estimation robustness, which is good for classroom settings and for museum settings, as I mentioned before. So what do you want to do next with this? With these kind of takeaways, I think that the right thing to do is to look into how we can integrate actually with the ARKit and ARCore illumination estimation. So GLEAM has some pros and cons. ARKit and ARCore illumination estimation has some pros and cons. Maybe we can combine the two. GLEAM's rapid light probe-based estimation with the rich but a little bit slow spatial sampling and the neural network-based approaches to give that robustness but also that richness. We want to look for more opportunities to optimize the performance and efficiency as well. So the kind of parallelism of looking at each of these pixels, we're doing it kind of not in the most optimal way. We could be using GPU compute shaders to do what GPUs are really good at. And we want to also reduce the overlap and redundancy in this shared and distributed sensing while we're trying to estimate the lighting from different perspectives. But I think what excites me the most is actually thinking about how we can explore the perceptual materiality of AR materials. The different materials that we want to use inside of augmented reality, these kind of marble materials, these metal materials, what is it that matters in order for the humans that ultimately receive this to actually get that sense of embodiment of these materials? Can we optimize for what matters? It's pretty unexpected in the future. Honestly, it's a little bit difficult to show through the screens because it's not just what you see in the screens, it's actually everything in your environment as a human that you experience. You want your virtual scene to match that as well. And so I beg you to please come and check it out at the demo session right after this session. But for now, I'll take any questions. Thank you.